just a quick review of what we've done so far is in Chapter 8 we looked at testing inferences from a single sample. In Chapter 9 we're going to talk about two samples, and we're going to look at testing if two proportions are actually the same or different. Then we're going to talk about two means from different populations. That's 9.3 with independent samples. And then 9.4 we're going to talk about dependent samples, samples that are purposefully matched. And then again, we're not going to do 9.5 in this chapter. So in Chapter 7 we talked about confidence intervals. In Chapter 8 we did formal inference testing of one sample. We used z-tests to test for proportion, and we used t-tests to test for mean. And they were all single samples from single populations. So what we're going to do in Chapter 9 is we are going to do inference testing with two samples. Are these groups from the same population? Are they the same or are they different? So for instance, we might want to test the claim that when college students are weighed at the beginning and the end of their freshman year, the differences show that they gained 15 pounds, as in the freshman 15. Or we might want to test the claim that the proportion of children who contract polio is less for children who had the Salk vaccine than for children given a placebo. And this actually was a test that was done in the beginning with the polio vaccine. We might want to test the claim that subjects treated with Lipitor have a lower cholesterol level than subjects given a placebo. So again, we're going to talk about inferences about two samples. And as we have in the past, we're going to start with proportions. So we're going to look at testing a claim about two population proportions. We're going to construct a confidence interval to estimate the differences between them. And then when we're talking about proportions, we can either talk about them with probabilities, decimal equivalents, we can even use percents, but we need to be consistent. Again, we have to have our notation. P stands for the population proportion. P1 stands for the population proportion. So we're looking at two populations, population 1 and population 2. So remember, the plain P is the population proportion, N is the size of the sample, X is the number of successes in the sample, P hat is the number of successes divided by the number in the sample, and then Q hat is the complement of P. And so subscript 1 stands for population 1, subscript 2 stands for population 2. Now, when we do this, we used a pooled sample proportion. And we use a pooled sample proportion because if the null hypothesis is true, these two samples that we have actually come from the same population. So we are adding P line, a pooled P and a pooled Q. So let's just talk about those just a little bit. So our pooled P is going to be the total number of successes over the total number of trials. And we do this because if the null hypothesis is true, there aren't two populations, they're just two samples from the same population. Now, what has to happen in order to do this? Well, we have to have proportions from two independent simple random samples. That means that one sample cannot influence who was picked for the other sample. A big clue, if you have two independent simple random samples, would be that the numbers are different. And then for each of the two samples, we need to have at least 5 successes and at least 5 failures. And that's for each of the two samples. And here's the equation that we're going to use. Now, our null hypothesis is always that the two proportions are equal. And we're going to look at our sample proportions and find their difference. And then we're going to look at the proportions that we assume are true in the null hypothesis. Well, if P1 equals P2, then that difference is 0. So this value is usually 0. And then our denominator is our pooled PQ divided by the number in sample 1 plus the pooled PQ divided by the number in sample 2 and the square root of all that. Don't get the hives looking at this equation because we're going to use StatCrunch. Again, we're going to use StatCrunch so the p-values will be available to us. If you don't have StatCrunch available to you, this is a z-test. Let's back up. This was a z-test. So remember, because this is a z-test, we're going to use table A2, and we'll be able to find those critical values quite easily. Now remember, in chapter 7 we started with confidence intervals, and that's where we're going to start with the two sample confidence interval. So notice that we have our assumed, or we want to estimate the differences between the two populations. So we find our sample differences and add our margin of error, or we find our sample differences and subtract our margin of error. Confidence interval. Our margin of error is going to be our critical Z, and then we're going to use our sample data here. So we're going to use P1 times, P hat 1 times Q hat 1 divided by N1 plus P hat 2 times Q hat 2 divided by N2. We're going to add those together, take the square root, and multiply it by our critical Z for our margin of error. And that's what we're going to add and subtract to the differences of our sample proportions. Okay, so here is an example. The question we want to answer is, do people having different spending habits? That is not written right. Do people have different spending habits depending on the type of money they have? 89 undergraduates were randomly assigned to two groups and were given a choice of keeping the money or buying gum or mints. The claim is that money in large denominations is less likely to be spent relative to an equivalent amount in many smaller denominations. And let's test the claim. Remember, let's test the claim. Aha, I'm going to do a significance test. So we have people who were given $1 and people who were given 4 quarters. You can see that in group 1, the dollar group, 12 spent it out of the 46. When people were given 4 quarters, 27 spent their money versus out of the 43. So we have P hat 1, P hat 2. And here's our pooled P. So, did we meet the requirements? Well, we had 89 subjects. They were randomly assigned, so they're independent. The other thing, remember, that you can tell when they're independent is, notice we had 46 in the dollar group and 43 in the 4 quarters group. When the numbers are different, they have to be independent samples. And then we look at the number of successes and failures in each group, and they're all above 5, so we are good to go. So let's look at our claim, and again, I'm crossing those out. I'm not highlighting them. Step 1, we're looking at our hypotheses. If there's no difference, we would write P1 equals P2. We are thinking that fewer people in the dollar group are going to spend their money than in the 4 quarters group. So P1 is less than P2 are our 2 appropriate hypotheses. And then this is step 2. And this is going to be step 3. So let's summarize our data. P hat is going to be 12 out of 46. P hat 1, P hat 2 is 27 out of 43. I think I would go ahead and find the decimal equivalents to these. We've got our pooled P and our pooled Q. So now we have the numbers that we need to go on and actually calculate our test statistic. And remember, this in our 6-step test, this is step 4. And so we plug in our numbers and we get a z-score of a negative 3.49. Now, what does that mean? When you're looking at this, it's going to be a good idea to draw your distribution so that you have an idea of the part of that normal distribution that you're looking at. So this is a left-tailed test since our z was less than 0, and we can calculate the p-value of that statistic. Now we would do this using StatCrunch or Table A2, or we can find our critical value using Table A2, which we'd look up at alpha equals 0.05 for a one-tailed test. We'd find our z is our critical z is 1.645. Since we're doing a left-tailed test, we would know it'd be a negative 1.645. Our test statistic is further out in the tail than our critical value, or our p-value is less than alpha. So this is part of, I would say this is still part of step 4. And then here we have step 5. I'm going to reject the null hypothesis. And then, so this is step 5. And then this is going to be step 6. And your book says there is sufficient evidence to support the claim that people with money in large denominations are less likely to spend relative to people with money in smaller denominations. Now, that's a wonderful summary, but we need to remember that we did a sample of undergraduates. And so we need to be cautious about generalizing it to the entire population. And maybe a better summary would be, there is sufficient evidence to support the claim that undergraduates with money in large denominations are less likely to spend relative to people with money in smaller denominations. So let's go to StatCrunch and see how that works in here. Okay, let's go to StatCrunch and let's do our problem here again. And so we're going to go to Stat, Proportions, 2 samples with Summary. And so in sample 1 we had 12 out of 46. And remember that was the dollar group. And sample 2 was that 27 out of 43 spent their money. And we want to look for our hypothesis, and okay, here is what it says: P1 minus P2 equals 0. That's the same as on the slides when it said P1 equals P2. We thought that P1 would be less than P2. So if we take P1 minus P2, that's going to be less than 0. And let's go ahead and compute. And you can see what we have here, where here is our sample difference. Here's our z-statistic. Our z-statistic is rounds to the exact same thing as the by hand calculation in the slides, and the p-value is the same thing. So you can see how easy it is. I want you to be familiar with the equation and why it works, but don't feel the need to go through all the pieces to get your z-score by hand, because what's going to happen is you can make one little math error and you're off, and then that means that your conclusions could be wrong too. So feel free to use the technology to do these things. The mathiest things that we just did here was right here when we change P1 equals P2 to the statement P1 minus P2 equals 0, and that P1 is less than P2, meaning we have a little number minus a big number, my answer is going to be negative. So this adjusting our null and alternative hypothesis was the mathiest thing we did in that process. Okay, now we could also do a confidence interval to estimate the differences between the proportion. Now, this is one of the things that we need to be cautious about. We use an estimated value of the population proportion. So when we look at confidence intervals, that we might get a different answer than that based on a hypothesis test. So my recommendation to you is, when you are going to test a claim, you want to use a full hypothesis test. When you want to estimate the difference between, then use a confidence interval. So let's go ahead and let's construct a 90% confidence interval, and we want to look at the difference between the two proportions, and what does that estimate tell us? So again, here is our formula for our margin of error. We're going to plug things in, do the math, and remember we wanted a 90% confidence interval, and you can find the 1.645 on table A2. And remember, this is our basic form when we set up our confidence interval. And so we get that our confidence interval is between a negative 0.528 and a negative 0.206. Notice that 0 is not in there. So this does imply that there is a difference between the two proportions. And since it's negative, that means that population 2 spent their money more often than population 1. So again, we do get the same conclusion here, that there does appear to be sufficient evidence to support the claim that money in large denominations is less likely to be spent relative to an equivalent amount in many smaller denominations. Okay, now I'm going to tell you this is going to be something I'm going to talk about quickly, and you don't need to have why do these procedures work. But here is the equation for our standard deviation, and we can estimate the standard deviation using this, and that's why we put all this under the square root sign, and that's why it works. So, just know it works, and we're good, and that's okay. Now again, use this caution. The p-value method and the critical value methods are the same, but you only want to use the confidence interval when you want to estimate the differences between the two proportions from the two different populations. Let's look and see how we do a confidence interval using StatCrunch. We're going to use the same data, and so we had the dollar group was sample 1, and we had 12 out of 34, 12 out of 46 spent it, and 27 out of 43 spent the 4 quarters. Now we're going to go down here for the confidence level, and remember ours was a 90% confidence level. So we're simply going to do compute, and you can see that we have our sample difference, our standard error, and here's our lower limit, here's our upper limit. And how do we find the estimate? The estimate is going to be the sample difference that we have here. Or you could find the difference between the lower limit and upper limit and divide by 2. But it's that easy to find the confidence interval on StatCrunch.